Indeed, I want to talk about game theory, and I want to talk about cancer, and I try to squeeze some machine learning into it, and you can tell me how I managed, okay, at the end. So I will start with motivation. It's a bit blurry picture on the screen, but what we are watching here is a cross-section of someone, yeah? So we are seeing here, in the middle, the organs, which are sadly surrounded by tumors here, okay? TKI, that's tyrosine kinase inhibitors, that's one of yet another drug which got Nobel Prize for its development, okay? And we see that if we apply it, the tumor decreases a bit, right? We see it shrinks a bit, even like visually, okay? But if we wait a few months more, the tumor stops reacting and is even worse than in the beginning. So why is that? And what I try to convince you by equations, but also images which simulate what these equations say, is that it might be because the doctor's lack of tactics with trying to treat this. Because the way how we now do it, we really sort of, according to this kind of war of cancer, right? We try to really pour on it as much toxic treatment as possible, okay? With this kind of hope that we actually kill all the cancer cells as fast as possible, okay? And we do it until we realize the patient is cured, or if there is inevitable evidence that the tumor doesn't respond, okay? In other words, if it looks like this, because often we don't measure it often enough, so we realize it too late, okay? And now, if you should remember one thing, what I want to say from the first slide, or slide second, is that maybe doing this is not as smart, that maybe we do not really lack new drugs, but maybe what we lack is tactics, okay? And now how does this relate to game theory? How many of you know something about game theory? Can you raise your hand? Okay, that's quite a lot. Very nice, yes? So basically, if you followed any game theoretical course or see, I don't know, Beautiful Mind or some movie about that, then you probably know that any game is defined by three things: players, strategies, and payoffs. And in order to call it a game, then the payoffs of the players have to depend not on their own actions, but also on the actions of the others. Example, I am a player. I try to make you all start doing game theory with your super skills, okay? You are listeners here. You have some objectives, maybe to get to the end of this conference as fast as possible, or maybe to learn as much as possible. It depends on you. My strategies are talking in some way. Your strategies are listen or not, or looking on your laptop, whatever you like, or escape at some point, right? But those outcomes which you want to achieve, I really don't know them, but they will likely depend on what I do. And the way how I will speak will a little bit depend on what you do, right? So it is a game. The fact that we call it a game doesn't mean that we can actually do something with it, but maybe we can use some methods which will help us to analyze what is the best strategy for me to convince you that you should all do game theory, for example, yeah? Maybe I should not use too many equations because it's end of the afternoon, etc., right? Okay. And then basically, one thing I forgot. In fact, from this perspective, also cancer is a game, because you have different cells. Those cells mutate. They don't do it thinking about it. But if they achieve some properties which will make them weaker than the others, they will die off. So likely, those who grow faster are going to survive, and those who grow slower are going to die in the long term. So basically, it is not anymore this game about strategies, what I think I should do if I try to convince you of something. It is more a game of natural selection. So what properties I should have, which are now my strategies. Should I be more aggressive? Should I be bigger? Should I be smaller? In order to proliferate and survive in an environment where I interact with the others, okay? And now, actually, my lab is interested in these games between human, us, very rational player, right? We can reason, we can think ahead, and the nature, like evolutionary systems which sort of adapt to our actions, but they cannot reason about it, they cannot anticipate, okay? And the classical game theory started with our joint hero, I think, von Neumann and Morgenstern. One of them maybe you also know from your textbooks, right? And then we have Mr. Nash, and my favorite one is von Stackelberg, because he was interested in how, if I want now to lure you into something I want you really to do, how do I do it? And preferably without you noticing, okay? And these games are therefore called Stackelberg games or leader-follower games, where I am leader because I'm imposing something on you, and you are adjusting to it, okay? And then there are these evolutionary games. They started, I think, with Darwin, because he defined these properties under which organisms survive under natural selection. But then the first guys who really came up with mathematics of it were Maynard, Smith, and Price, who were sort of looking on how animals fight between each other and what properties they have to have in order to win, okay? And so just to repeat, in the classical game theory, you are interested in rational decision-making, what is smartest to do, if I anticipate what you are going to do. In this kind of evolutionary game theory, the question is, what properties should I have in order to survive in an environment where we fight together with other individuals, okay? And I'm interested in those connections between these two worlds. So if I, rational leader, enter this evolutionary followers world, can I steer them into what I want them to do? We are quite successful in extincting many species, right? So that's not so difficult, right? Yeah, we did the right thing there, if that was the goal. Now, of course, the question is, what is your goal? And we are using, on one hand, we are interested in the theory, so under which conditions I can achieve what I want as a leader. On the other hand, we are modeling things like, why, if I am fisheries manager and I try to maximize my profit, if I really keep fishing as much as possible, then I will get a much lower profit because the fish will shrink, right? They will adjust evolutionary to this. So then at the end, you distort the fisheries and you have no profit, right? Or in pest management, right? If I apply too much pesticides, what I will actually end up with are pests which are resistant to everything. And of course, there was this resistant management crisis in the last century in America because we poured all possible pesticides on some insects, and then we realized that they can live under those conditions, right? And they will just grow exponentially, yeah? And of course in cancer, and that's what I will talk about. Let's see how much time I spent on intro. Quite a lot, right? Yes. And basically, we termed Stackelberg evolutionary game because we have the Stackelberg leader, and we added them into evolutionary followers. So here's a small commercial for my paper. And then the question is, if it's like this kind of evolutionary system, right, it will sort of adjust, and there will be some trajectories, how, depending on what I do, maybe number of fishes will go up or it will go down, and maybe some of these fishes grow and some will go down. But the key question is, if I would want that these trajectories end up in this box, is there a way to do it? So if I would want either, in case of fish, to keep them above a certain level, and in the case of cancer, maybe kill them, or at least contain them under a certain level, can I do it? And is really using the most aggressive treatment possible all the time the best way to do it, okay? And so we get this scheme. So basically, we talked already about that cancer is a game. How many of you did I manage to convince? Few? Okay, we would need a few more minutes, but I want to progress, so I will try maybe next time with the others. Okay, that maybe doesn't help us as much, but so we are sort of imagining we can model it somehow. We can probably imagine how they will respond to each other. You know, if I kill one, the other will grow, things like that. Cancer cells have different types. They adapt, so there will be more and more types maybe. And then I added this physician. I treat. The cancer cells respond, right? I treat. The cancer cells respond, okay? Maybe we should observe it somehow. That's not what we do, right? What we do is we play all the time the same action. And then only once we realize it doesn't work, we go to the other action. So if I look now on this game, on the interaction between the physician and the cancer cells, so we know that this is an evolving Darwinian system. So it's goal is to proliferate and survive, where we are sort of hosts. We are the planet Earth, right? And it's a new life form, okay? And then if I ask physicians, what are you trying to achieve with this super aggressive treatment? They will tell us, what will they tell us? What do you think? We try to cure the patient, right? And of course it works if you have just really one tumor, then it makes sense to sort of remove it. Yeah, it makes sense. But if it is like a cancer which spread overall in your body, it is, and then I ask them, how many of your patients do you cure? And they will say, none, they are all palliative. And I say, so how do you do it? And they will say, I apply the same treatment, I wait until I realize it doesn't work, then I take a different drug and I apply that drug until it doesn't work, right? So, right, killing all the cancer cells at this moment is not the same as keeping the patient alive tomorrow, right? Okay, and then what we try to convince them of now is that there are two critical asymmetries. Maybe I already convinced you, so you don't need it. You are smart, right? So one is we are rational. Cancer cells are not. Yeah? If we know that every single advanced cancer will evolve resistance to my treatment, maybe I could think ahead. What would be a different strategy? And then the timing. Of course, a physician will always tell me cancer was here first, right? But I mean, I am sort of resetting the conditions for this evolving system every single time when I apply a new treatment, right? So in the same way as we managed to extinct a lot of living beings, how did we do it? We sort of tried to decrease their number, and then once they were really, really low, then something unexpected happened, like earthquake, fire, and that was enough, right? But here we just apply the same action all over again, so, okay? So we sort of use game theory, and there are like theoretical results which actually show that if you try to reason about it a little bit more, you can achieve much better outcomes, and I hope I will convince you of that in the remaining time. Okay, and now first equations, but there will be also pictures, yeah? So this is like the really simplest possible model I can think of, how we describe a situation when we have these light green cells, almost white ones, which would be fully sensitive, for example, or more sensitive to treatment, and a bit darker ones, which would be resistant, okay? And the simplest model we use, actually, they have the same dynamics in a sense, and the only difference is that the treatment kills more those cells which are sensitive than those cells which are resistant, okay? And then there might be some other differences. And then we also assume there is this K, which means that they actually share common space, okay? Or they share common resources. And then actually, it doesn't matter what are these assumptions here. There are some typical growth you can assume. You can change it to not 2 types, but 20 types. But in fact, what will happen if you apply this maximum tolerable dose? You will basically kill earlier or later all the sensitive cells, and the tumor will become fully resistant. There is no strange thing happening because you are killing those here much more, and therefore these ones grow more, okay? We do this with, say, hormonal cancers, because there we know that some cancer cells react to the hormones, some others not, so we remove the hormones, and that's what typically happens. And then we try something different, and we repeat, okay? If we take different model, just different assumptions, doesn't matter. That, there are typical models which are used. If you just assume that there are 2 cell types, again, they use the same carrying capacity, so means the same space. The same thing will happen to the system again. So it doesn't really depend on the model. You will always see the same thing, okay? And then there are cancers which we have absolutely no clue whether there are like distinct types which are sensitive or resistant. So then we use slightly different models where we basically assume there is one population of cancer cells, and there is some resistant trait, which means the cells are not either fully sensitive or fully resistant, but basically they can gradually become resistant, yeah? So it might be that each of them has a chance to become resistant through acquiring mutations. And at the end, again, with the same treatment, you can always very easily show, and I could show you here simulations, but it doesn't really matter, because I think you already understand that this makes sense, that basically you are basically training the best enemy you could have if your goal is really to contain them, right, or keep them under a particular level. And of course, the reality is much more complex than my models. So typically, we have multiple cell types. They can be either fully sensitive, fully resistant to a particular drug, or there can be something in between. So it will probably look much more than this, like this, than actually the idea that you have only two types, yeah? But the same principles hold, right? So I target one type, it will die, the others take over, right? Not very surprising. Maybe that's make it worse. So what I'm showing from our project on metastatic non-small cell lung cancer, what we see on the left side is all the possible resistance mechanism which we know of in the non-small cell lung cancer once I applied for long enough the maximum tolerable dose. So basically, there are some mutations which are known, but about 30 to 40% I don't know how this happened, okay? And if I apply the same drug as a second type drug, you get again, like really many options how the cells became resistant, and some of these reasons I understand, but let's say in 40% to half, I have absolutely no idea, okay? And here we are saying we are still looking for the silver bullet treatments which will really target this particular mutation and will cure the patient, yeah? So how likely is this, okay? Fine. So now I want to tell you there is hope, okay? While basically in the past decades, we really did not become better in treating advanced cancers on average. So we became much better in prevention. We became much better in treating early stages of cancer. For most advanced cancer, really, if you look on time to progression, from meaning until you really know that you can't, that sort of you lost the game against cancer, it remains for most cancers the same. And let's say in some types of prostate cancer, it's even worse, okay? In spite of new drugs, yeah? But I still want to come to this message, there is hope, okay? So it's called evolutionary therapy, and it's based on game theory. That's why I am talking about this, okay? So here we have this original picture. So the idea that basically we treat with the same dose, actually the maximum dose I could treat before getting really severe side effects, okay? And then the evolutionary therapy thought like, okay, let's do something different. If the problem is that I kill all the resistant cells, maybe I could treat a bit less, right? Or I can even try to have some pauses between the treatments, yeah? So then the idea is that you get these more dynamic protocols when you are really trying to sort of not kill all the sensitive cells. So I sort of treat a little. Once I noticed the tumor shrank to maybe half, for example, I stop treating and I let the the tumor regrow, and then I continue. The side problem is we are not anymore, here we know what is the goal. We are trying sort of to postpone progression, but this patient is never going to be cured. Yeah? So we are trying to make it chronic. Yeah? We are trying to sort of like stabilize it. But you could see that this is possible. So these are patients with metastatic castrate-resistant prostate cancer. And these black dots, on their body, those are all tumors. And they really go to bone, and it's very painful, okay? And so the first attempt to do this kind of evolutionary therapy, in this case called adaptive therapy, was that basically the second-line treatment, which was given at a maximum tolerable dose with terrible side effects, on the top of first-line treatment. The idea now was that I will treat only until basically the tumor shrinks to about a half, which is measured through a particular biomarker, which measures the tumor volume. And then you let the tumor regrow. And then you do it again and again. And this first trial was very small. It was really just to check whether these patients will remain stable. And what was really interesting was not only that all these patients, most of these patients had survived stable for much longer than on the standard of care, but also if you see these red and black colors, the red is the time on the treatment and black is off the treatment. So actually every single patient had a different response to the treatment. So it took them longer or shorter time until their tumor burden went to this half, okay? And if you compare the time to progression, so these are Kaplan-Meier curves, the medical guys love it. It sort of estimates how many months you are going to live. The patients in this initial trial doubled to tripled the time to progression compared to the standard of care. Okay? And because it is now so successful, there is another trial which repeats it, and there are many other cancers where we repeat it. And that was based on this kind of game theoretical model of cancer and how does it respond to treatment. And now we have different options. So adaptive therapy I was explaining, so you either decrease the dose or you have these pauses in treatment. And the idea is then, I know that eventually I might be leaving this green box, so the safety box for the patient, but I either try to postpone it by this kind of treatment on and off, okay? Or I try to stay in this green box forever by maybe hitting this kind of equilibria of the cancer cells, okay? And then what seemed to be science fiction for these advanced cancers, but their first successes is called extinction therapy. So really applying the lessons we learned by extincting so many other species in cancer, okay? So basically, once there is this initial response to particular treatment, you do something really unexpected, you know, like crazy immunotherapy, something really strange, the earthquake, okay? So here in this goal of postponing progression, in this trial I was showing you, the key problem was that you sort of would start somewhere here maybe, and you would sort of cycle with your trajectory of cancer cells outside to the box until the cancer progressed, but you would miss maybe equilibria of the system if there were any, so if there was a chance to stabilize. But if you now would look on like how the treatment, if you would average all the treatment over the patients, then you would end up with protocols which are called either gradual dose decrease or gradual dose increase. And it works as follows. Basically, I start either with a maximum tolerable dose, and I decrease it a little bit until the tumor stops responding, and then I increase it a little bit, okay? So I'm sort of trying to tune it. So if the tumor doesn't respond, I have to increase the dose a little bit. If it responds in terms of like how big it is, okay, then I decrease it a bit until I reach stabilization. And now there is a large trial in UK for actually all patients with ovarian cancer at a particular stage, where they are trying to do just this, okay? To stabilize them forever, because these ladies are maybe 70 years old. So if you would manage to manage this for 20 years, you have sort of won, because then they will die of something completely different, okay? And maybe even better is to start from much, the minimal dose. Okay, this was a bit strange how to put it here, but you see what I mean, right? So that we cannot prevent that they die of something different, right? But the point is that you could also start from really minimal dose if you have the time. Then you say, okay, the tumor doesn't respond yet. So I will sort of increase the dose a little bit, and then I stabilize after a while, okay? Now we can do this relatively well in hormonal cancers, but there are these much more aggressive cancers, like this non-small cell lung cancer I was showing you. And there we sort of believe we cannot do it with one drug. So the idea would be that maybe we could really do strategic application of two drugs, such that we can stabilize the tumor forever. Forever, yeah, okay, again. You see what I mean, yeah? And for that, we are using a clinical trial when we have not only standard of care data, but also blood draws, so which actually gives us circulating DNA cell. I should look natural now, right? Okay. Picture. Yeah. Sorry. Yeah, okay. And basically, within this, so like the normal data which we get is something like idea of what is the tumor diameter over time. Yeah, so it's very, very coarse. And then we try to fit it to these models I was showing you. Yeah. And now on the top of it, we are getting new data which are actually taking blood from your, just the blood very frequently. And you are trying to see whether these tumors do not shred DNA cells, which can tell us something about compositions of the tumors, okay? So we basically work on this problem, but now with much more aggressive cancer. Then we try to see whether actually we can use this data, which tells us something about the composition of the tumor, to really decide better about the particular model. First time when I talk about machine learning here. So our models are equation-based. So then we are comparing them to machine learning algorithms in terms of prediction of time to progression for the patients. Because if our explainable models cannot really predict it well enough, or as good as machine learning models, then likely we are missing some assumptions. So then it's like sort of chicken egg problem where we try to adjust them, okay, with additional elements in the model. Okay, Nice. Then when we have this, then the key question is, we understand what is happening on standard of care. Then the question is really like, what are we trying to optimize? Yeah, so can we really achieve cure? Not yet. Can we stabilize? And then we are sort of suggesting to each patient something like, if you want as little toxic treatment or as the least toxic treatment possible, this would be the best way how to do it. If you want to really try it as aggressive as possible, this is the likely outcome, but you can try this, okay? And if you want to stabilize your tumor forever, this is the most likely scenario. So moving to more also what the patient wants as opposed to the doctor wants, which is typically the most aggressive treatment, yeah? Okay, and then basically we are developing a new game theory, which is maybe on different talks, so maybe next time, who knows? And they are having names, so there are 3 youngsters who are working on this with me. And then, of course, I was talking about these liquid biopsies. So this is really sort of, I don't know if you can read it. So what we are getting now is like really what is the frequency of particular mutant in the blood, okay? So here we, for example, see that we have the treatment with this kind of tyrosine kinase inhibitor. That's one of these novel treatments which we had before. And you see that basically the goal is to really keep some of these mutants down. But we see that at frequency, because this is like how many milliliters of the blood you take and how big portion of it is the particular mutation, then basically you see that some of them goes up. And then here, because we don't know what was the reason, the standard of care is you apply maximum tolerable dose of chemotherapy, for example, and you see there is like an initial response, and then it grows back, okay? So now the question is indeed, if I know this, can I actually do something different? And what we are almost always ending it are these protocols where you apply one treatment, then you surprise the disease, and you try something different, okay? And now this part which I would call, wow, right? And maybe all these issues which we have with data, and there I think that I could also use a lot of your superpowers, so I already work with some machine learners, but the issues we are having, okay? So there, you know, the hope is there. Even with simpler models, we can actually see that we can already improve the treatments, but then there are the standard problems, which you maybe see in the medical world. So this is how our data looks like, right? So these are tumor diameters over time, if we do not think of these liquid biopsies, yeah? So we can fit them to different models. So here, this is an example of the project where we can fit them, yet, you know, it's again 2 types of cell types, and they have some different growth than we expected before, because there is a reason why to believe that's the type of growth they take from in vitro studies, for example. And then basically we take a lot of patients from different clinical studies, and we try to now figure out whether this model fits this data well, and whether it can also predict the future time points for these patients, yeah? Initially we had 1,600 patients, but once we required that we want at least 6 time points, we ended up with 587, okay? And then, of course, we can, with almost any reasonable assumption, we can fit this data well. This doesn't necessarily make it the right model, right? So what we cannot capture with these models is so-called delayed response, when the patient first doesn't react, and then only later it goes down. So that means there is something missing. We have to add it, right? But in the situation where I have such a trend where it's, for example, only decreasing, I can actually fit it to any model I like, right? So the question one is, what do I do if I have 10 plausible models which all could explain what is happening to this patient, okay? Here is another model to which I can fit exactly the same data. And it actually can perform much better than what medical doctors use, because they often use linear regression, right? But, so that's improvement. But it's a completely different assumption. Still, I can fit it well to my data. So if I, again, look on different multiple clinical trials, the game theoretic model always outperforms the standard models which is being used in the field. But what is the exact assumption? It's enough to either assume that you have 2 cell types, or that you have resistance which evolves. Okay, so if you have this assumption, it will all work well. How many minutes still? 10, okay, it's not too bad, okay. So the possible problem, which I probably hint already for 10 minutes on, is, this is von Neumann's statement. With 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. Do we believe it? So there is even a publication on this. I found it recently, thanks to Jeffrey West, who is like one famous figure in oncology, which is called Drawing an Elephant with 4 Complex Parameters. Yeah? So if the parameters are complex, you can even make the elephant wiggle their trunk. Okay? So now, do we need to test all plausible models, so that's infinitely many, to fit the volumetric data well and to test the best treatment strategies? What do you think? Any hints? It's a bit late in the afternoon. Huh? Okay. So for some, we have theoretical proofs. So in some case, maybe still yet, what is the possible issue, right? I can say, okay, I will choose just my favorite model. That's not a problem. So there was this publication in Nature, Ecology, and Evolution, which said, we found the right model to fit this data. It's data in the Petri dish. So you actually can even have cell counts of the resistant population and the sensitive population, okay? As opposed to in a human body, where we are sort of trying to estimate it. We don't know that. We can measure only like some of them, and we try to estimate what is the sensitive and resistant subpopulation from their response to treatment. So here it is a simple situation because you have both of them. So this paper basically said, okay, this is the model because it fits well, and it made a number of claims on what does it biologically mean for this particular cancer, by chance the same one I'm interested in right now, okay? And we took this exactly, completely different model. We tried to fit it with our comparison model. So that's, again, 2 population, a different assumption than the guy had. And we could confirm only one from the outcomes of this guy, okay? So the only thing which we could confirm was that a particular different type of cells actually decreased the effectivity of the treatment. But his main claim was that these resistant cells become much more aggressive in the presence of sensitive cells, and we could not really confirm that. So the problem would be if each of these models leads to different treatments or to different outcomes, right? Because then you would really have to test the whole range of the models. And that's why, again, opportunity for machine learning comes in, right? So then, similar to our liquid biopsies, you can think of any omics data which you could actually use in order to give you maybe a better idea about which of these models is certainly wrong and which of them is certainly right, okay? And smoothie. I always like smoothies in the, in the talks. So, but the problem is, for some of these cancers, we really do not know what these types are, right? Because we just are interested in how do they respond to our treatment, right? So whether or not they decrease in size or they increase in size, right? So in a way, in some cases, like breast cancers, prostate cancer, we really know what is the profile of the resistant cells, or we might at least know some mutations, okay? In some other cases, it's really sort of like looking for different, you know, that you really get a smoothie, and then you are trying to find what were the profiles of different fruits. Well, some of these fruits you never saw in your life. So there we can apply non-negative matrix factorization, for example. But the problem is that as many types I want, I will probably find, right? So that might be sometimes a bit of issue, but it helps us to sort of at least exclude the models which completely do not make sense, right? So those which, for example, assume that there are no sensitive cells where there should be some, etc. Okay? So we do it through tests which we cannot necessarily do inside of the patient. And that is through organoids, that we basically take a tumor, biopsy, we create from it, we grow from it a new sort of organ. This is called organoid, which actually grew from this tumor. And then we are trying to see whether we can actually estimate what are the different cell types, such that this would help us to have the proportions even better, such that I can choose really what is the right model which will guide my treatment in the best possible way. Okay? And then, of course, the common problem, we typically, if I ask for time series, this will mean 3 or 4 time points. But that's already a very good way forward to really exclude the completely unreasonable assumptions in our models, which are all equation-based. Yeah? And then basically, Sometimes the question is really like, what is an average size of the sensitive and resistant cells? And this we can do relatively well already from these biopsies. Possible problem is, of course, that we have many of these tumors, and probably each of them has a different composition, and you are not always able to actually get the composition of all of these tumors, while if you take it from the blood, then you have this kind of average composition of all tumors together, okay? But at least it's better than nothing, so we have a lot of ways how to improve. And then, of course, the other option is imaging, which we cannot get for the lung cancer, but maybe for colorectal cancers, this is one of the cases where you can actually take the images, where you basically mark particular cell types, because we have relatively good markers. The problem is that it's not going to be yes or no. So this is like really part of the tissue. And then you are evaluating which pixel has a particular expression of a particular marker, which would define it as, for example, as an immune cell or cancer cell or more sensitive resistant cells. And then you really often end up with a huge number of cell types which are differing in their profile, okay? But then what we then do is we collapse them together, and then we can again estimate what on average is the size of the sensitive and resistant population, which means we have to be relatively conservative in our optimization suggestions, right? Because if we are wrong, you don't want to really, get this undesirable result when instead of extincting the disease, you extinct the host, yeah? So I did my best to show you a bit of machine learning combined with game theory. I hope you don't ask too many technical questions, but let's see. What I would want you to remember is, if I convince you of that, of course, is that this idea of the doctor versus treatment, this is really like sort of leader-follower game, and we should be in the lead. Maybe we should teach our doctors mathematics, maybe also some machine learning. Then physicians can exploit it, they just don't do it yet. It takes really long of time. Often if I talk to them and I say, you know, this adaptive treatment would be better, then they say, well, but explaining it to my patient would take a time, right? So that's another problem, but that's outside of this talk. Then, of course, what is the treatment goal is a question, because if you have any evolving system and you want to lead it to somewhere, depending on the objective you have, you would end up with different strategy. So the first question to ask yourself is, what do you want to achieve for this patient and what the patient wants themselves? I strongly believe that, at least from the initial evidence, we can use machine learning and we can use data, the additional data which we have, but it's still very messy, right? Because we are sort of in very early stage. These liquid biopsies are nowadays used to just identify that there are some mutations, and they are not used to estimate the proportions, for example, of these tumors. Yeah. So we are trying that, and that should lead to better models, or more precise model and more individualized treatment. And of course, now the goal here is to stabilize the tumor for as long time as possible, so really making cancer a chronic disease. While the next step is indeed, this is really a paper focusing on extinctions and the lessons we learned from them, is once I really understand the system well enough, if I know that the typical trajectory is that first it goes down, the tumor burden, and then it goes up, then what is this moment in which I should apply some completely different treatment so that I really drive them into extinction? So at Moffitt Cancer Center, they have this Center for Evolutionary Therapy where they can try it for like individual patients. And, but it's not really yet tested in any clinical trial because every patient needs actually a different protocol to achieve this. Okay? So, but I really strongly hope that once we can make all the cancer chronic, the next step is going for these extinction attempts. And this is a really full slide where I want to thank the team and also to you for your attention.